Howdy! Welcome to another solution for Ted Shifrin's Multivariable Mathematics. We're going to be looking at problem 1.3.4, which is Chapter 1, Section 3, problem number 4. Let's take a look. We want to show that I think it's pronounced V-perp is a subspace. So just to refresh our memories, what's V-perp? If you remember from the section, it's defined as the set of all x's such that x dotted with v is equal to 0 for all v and v, where v is a subspace of Rn. So if you have some subspace of a vector space, so let's say my subspace is v, it's orthogonal to this set here, v perp, which is defined as the set of all x's that are orthogonal to every element in v. That's all it is. It's just take everything that's orthogonal to everything in V, and that is the perpendicular complement. Let me see, it is the orthogonal complement. My mistake, yeah, the orthogonal complement, and I think we call it V-perp. Okay, all right, so let's show this. We want to show that it's a subspace. Proof. So let's start off with what we need, our ingredients. Let V be a subspace of Rn. And it doesn't really actually have to be of Rn. It doesn't matter, any inner product, whatever. OK, the field can be anything. So let V be a subspace of Rn. Let's also let V be in V and W be in V-perp. The following hold for all v and v. Okay, so there's actually a bit of a nicer way to do this, but we're going to go sort of with the straightforward method of doing this, right? Okay, we want to show it's a subspace. So in effect, we're just showing it's a vector space. That's really what a subspace is. It's a vector space in a vector space. But we have the added benefit that knowing that, the space that it lives in is a vector space. So there's a whole bunch of these axioms we actually don't have to show, right? We don't have to show, that this is true. All the vector space axioms, a lot of them are taken care of by the fact that Rn is already a vector space anyway. So there's three things that we need to show to establish then that this subset is a vector space. We need to show that the 0 is in there. We need to show that it's closed with respect to addition, and that it's closed with respect to scalar multiplication. If we can show those three things, we've established it's a subspace. So that's what we want to do here. I want to show that 0 lives in this set. I want to show that if I take two elements of this set and I add them, I get back another element of this set. And I want to show that if I take a scalar multiple of an element of this set, I get back an element of that set. And then I'll have shown that that's a subspace. So that's what we're going to do. And we just kind of gave ourselves something to work with here. I have notation now for a vector in V, and I have notation for a vector in this orthogonal complement here. And this is just so I don't have to keep writing this statement for all V and V, because we are going to need to show that it's true for all V and V, but to write it over again and again and again is tedious. So I'll just take care of that statement once here. And all three of these properties should hold for all v and v. Or at least, maybe not all three, but where it's relevant. OK, because right here you're going to say, it's true for all v and v, but, well, yeah, whatever. OK, so at first we want to show that 0 belongs to this set. So we're going to do 0 dotted with v. What's that? Well, that's 0, right? And that's true for all v and v. So 0 belongs to V-perp. So 0 by definition, right? If it's a vector that's orthogonal to everything in V, well, 0 is orthogonal to everything in V, then it's an element. So it's in there. OK, now let's take, and I know I put W here, but we're going to use a slight modification of that notation. But it establishes what we mean, so we get the idea. I'm not going to take the time to rewrite this. So we're going to say, let's take W1 plus W2. Clearly, these are elements of V-perp, the orthogonal complement. And let's dot it with V. Well, we know we can distribute the dot product, so we're going to have W1 dotted with V plus W2 dotted with V. But we already know that these two are elements of V perp. And what does it mean to be an element of V perp? It means this thing dotted with anything in V is 0, and this thing dotted with anything in V is 0. So when I sum them, I get 0. So for all V, this thing is equal to 0. And therefore, W1 plus W2, when I dot it with V, no matter what, so long as it comes from the subspace V, I get 0. That means W1 plus W2 is in V perp. And now finally, the last thing we need to see is that CW dotted with V is also 0 for all V, right? Well, once again, just pull this, redo the association here. So we're going to do C times W dotted with V by associativity, right, between scalar multiplication and the dot product. And we already know that W was an element of V perp, so I know that this dot product with any element of V is 0, and C times that 0 is just going to give me 0. And so it means that this CW must have also been in my set. And I've established my 3 properties that I needed to show that it was a subspace. Hence, it's a subspace. All right, that's it. That's the proof. I'll see you next time, folks.